Good afternoon to everybody. Here we are with a new lecture, public lecture within our Strong 2020 project. The project is an international project involving people from all Europe. And I'm Catalina Curciano from Laboratori Nazionali di Frascati of ANFN. I am the leader of the dissemination and communication work package within this project. And I have the very big pleasure to introduce today a lecture which is having as a title, Navigating Uncharted Territories in Strangeness, with Siddharta-2 experiment, which you can see in this slide, at the Dafne collider we have in Frascati. And here you can see the Dafne collider. Before leaving the floor to our guest of today, let me tell you some words about our European Strong 2020 project. So those who are here following us, you of course are already connected. That was the first presentation of our public lecture. But let me tell you, as I was already telling before, some words about the European project Strong 2020. This project is studying the strong interaction at the frontier of knowledge, and it's performing both fundamental research, but it's also looking into possible applications in various fields of importance for society. The project started already in June 2019 and has received important funding from the European Union under the Horizon 2020 program. The project itself brings together leading research groups and infrastructure from Europe, and it's having as a goal the study of the strong interaction, but also to exploit the innovative potential and application of the research for society, both in medical imaging and in information technology. The consortium includes 46 participating institutions, and it's embracing 14 European states in all our continent. It's also involving one international interest organization, which is CERN, and one European candidate country. There are other institutions of other 21 countries which do not receive European funding, bringing the overall number of involved countries to 36. We are divided in about 32 working packages. Some of them are providing transnational access to research infrastructures. Some instead are providing support to activities of research like networking activities or joint research activities. And also, the project offers access to world-class facilities set in Europe. Among these, there are COSI, MAMI, Frascati National Laboratories, where we are today, ELSA, GSI and FAIR, and also at CERN. There is also a peculiar support to ACT STAR in Trento, which plays a crucial role for fostering innovative theoretical developments in hadron physics in close synergy with experimentalists. These are the countries which are involved in the Strong 2020 project. And today we have a special guest, Dr. Fabrizio Napolitano, who is going to introduce us in the magic world of the uncharted territories, which are having to do with the experiments which are done in our infrastructure, Dafne in Frascati. And Dr. Fabrizio Napolitano is postdoc researcher within the Strong 2020 project at Frascati National Laboratories, and he is working in the field of strangeness physics and also in quantum foundation. Today, he will introduce us in the part of the research which is connected with the beauty of the exotic atoms which are being used from our accelerator to unchart the new territories he's going to present to us. Fabrizio, the floor is all yours.
Thank you very much, Catalina, and thank you for the invitation to this Strong 2020 public lecture. So today, as Catalina told, I will give a brief overview of this magic uncharted territories in the strangeness, which we are exploring with the Siddharta-2 at Dafne. And since we started speaking about uncharting territories, I thought it could be a nice idea to show on the background of this image what it is. One of the first atlas which was done in the 16th century. And something I always note as remarkable are the details of this kind of maps already in the early times of the exploratory geography, and also some peculiar features such as you see below in the south of the world this a large continent which was just hypothesized to be counterbalancing the mass in the North Hemisphere. Indeed, there is a continent which is down below, Antarctica, but what was here also missing was Australia. So this is also to emphasize this uncharting of new territories. And what I always like to mention in this kind of map is the quote from Cicero, and he wrote this now almost more than two millennia ago. Wrote these lines in his books, which loosely translates as the importance of the understanding the vastness and the infinity of the universe cannot be outdone by anything which we see on this world. And as a side note, I'm speaking now from Frascati, which was the place where Cicero wrote these books. And so I thought also that we can start from uncharting the territories in the world, from uncharting the Earth from space. And this you are looking at is called the Golden Record. For those who don't know, this is really a physical record, which was sent with two probes, Voyager 1 and Voyager 2, in August 77, on a tour inside the solar system. You see here on the bottom right, kind of the path with in all the planets of the external solar system that they visited, this Voyager 1 and Voyager 2. Voyager 1 is actually the farthest man-made object from Earth. And this golden record contains, for example, images of common life on Earth, contains greetings in many languages of the world, and there are instructions, as you see on the top part of the record, how to play this. This is kind of already built-in play feature of this Voyager space mission, which entered the interstellar space in 2013. And what I also would like to focus on this is this star-shaped object on the bottom. And this is actually very interesting because it represents the position of the Earth relatively to the closest neutron stars, which are called pulsars. So pulsars are very special stars because they emit radio waves with a very fixed and predictable frequency. So, for example, here on the right, just to give the scale of how to define this frequency, you can see the representation of the hyperfine splitting of the hydrogen atom, and this happens with a frequency of about 1 nanosecond. So with this time, really all these in binary, all these pulsars are defined. And of course, one can think that in the universe in general, there are many, many pulsars like those. but a combination of those unique pulsars with their unique frequencies, it's really hard to find elsewhere. And in addition to that, the frequency of the pulsar is getting slower and slower with time. So additionally to the position of Earth relatively to the pulsars, which means to a way to identify the pulsars identify the Earth from in the galaxy, it is also possible to reconstruct the age where these probes were sent. And also, when I first look at this image, I kind of thought that this really looks like a nautical chart. And here on the right, I'm putting the oldest nautical chart surviving to these days, and this is called the Carta Pisana. It dates from the 13th century. I try to emphasize a bit the contours of the Mediterranean. As you can see, this was found in Pisa, so maybe they were interesting, of course, in this section of the Mediterranean. But of course, we can draw the parallel that it's really striking with these objects. And indeed, pulsars can be used for charting known territories. But since we spoke about pulsars, I want to spend about a minute on some general information. So they are a class of neutron stars which spin very rapidly. They have their axis of rotation, which is slightly off with respect to the axis of their magnetic field, which is, by the way, extremely intense. So around 10 to the 8 Tesla. This is could be also more, and this is extremely can give an idea of the extreme condition of these objects, especially when one, for example, thinks about the world record for the the highest magnetic field which is reproduced on Earth, which is about 45 Tesla. So this is really an object which is well beyond the what we can achieve and could ever achieve on Earth, and in terms of magnetic field. And of course, this means that these objects can be seen. Their radio waves can be seen from very far away. And the neutron stars, which is the kind of class of the pulsars, are one of the product of the stellar evolution. So for example, here I'm showing the supernova remnant of Cassiopeia A, which you can see in the kind of nebula at left, with at the center the neutron star. So the neutron star is really an object which is was one step from a black hole. So the incredible amount of mass which is compressed in a small amount of space, it is actually really, really impressive. And so I wanted to maybe focus a bit on what it is, how it is inside the neutron star, because we know that of course, in order to balance this incredible pressure, many subtle nuclear phenomena become important. So the neutron star is called neutron star because the protons, they actually absorbed, so they underwent inverse beta decay. They absorbed an electron to become neutrons. And this is really in order to compensate for the incredible pressure of this inside those objects. And indeed, depending on the kind of nuclear forces which are in play, one can see that there are many scenarios playing out for the inside of neutron stars. And this is really frontier of what we know. So as I show you the traditional neutron star, but of course, depending, as I said, on the dynamics of the strong force, which connects the quarks together, then one could have a quark hybrid star where the strange quark is present, for example. This strange quark, we'll see about it also more in detail later, is very important for what we do here in Frascati and for this talk, and we call strangeness everything which is related to the strange quark. But we can also have more complex aggregation of these quarks in what are called the hyperion, so in the hyperion star. Other possible explanation can also involve stable, strange quark matter, for example, like in this quadrant here, but also a nucleon star where you see you have a kaon at the very core of this star. A kaon is still also a particle which contains a strange quark. And these stars, I told you, they are very compressed. In fact, their typical radius is about the order of 10 kilometers. So you can imagine in your everyday world, you perhaps do every day 10 kilometers to commute from work, from university, and so on. So one can really have the idea of the smallness of this scale. At the same time, the mass of this object, which is more than 1 time the mass of the solar system. The mass of our sun, the sun. And in order to understand which of these scenarios are the more plausible, of course, one has to study the inside of the nuclear matter, and this is an animation which is showing what it looks like inside, and we call quantum chromodynamics the theory which is behind the strong force. The strong force, as I said, connects quarks and gluon. And this is really different by the picture we all have naively in mind with the little spheres, which are the protons and neutrons, and they sort of stay fixed in the center of the atom, for example. And just to mention why it is so important to understand the mass radius relation of the neutron star, this is an example which shows as a function of the radius and the solar sun and the solar mass of the star, the possible dynamics which could go on based on, for example, a three-body interaction, which is with these strange particles inside. So you see on the top, you see two of the most massive neutron stars which were observed in our universe, and you see this becomes important because you can rule out certain kind of interactions if your theory, if your description of what goes on inside does not make this star possible. And so, since I mentioned a lot neutron stars and the content of quarks, so I also give you a brief overview of the standard model of particle physics, which describes all the fundamental particles we have in nature and we have observed so far. So you see on the left the building blocks of our matter, so which are the quarks. Up and down, they are found in protons and neutrons, and more generation you see on different columns, more generation ahead, the more these particles are typically massive, and their lifetime is shorter. And also what is called the leptons. So the leptons is a big family of the electron, for example, and the neutrinos, and so on. And so you see, we still focus on this strange quark and its connection with all the other ones, which we will see also later. One of these particle which contains strange quark is called kaon, as I said. And then in the standard model, we have the force carriers. So, for example, the carriers of the electromagnetic interaction, the gamma, but also the weak force, which are the W and Z bosons and the gluon. And all of these, they obtain their mass via the Higgs boson. And so I say these quarks, they make other particles together. And you can see on the left what are called, this is one example of other particles which are called baryons, and they order by their content of strangeness. So you see on the top, which have no strangeness, neutrons and protons, but also we have here other kind of all kind of particle which contain one or even two strange quark. These are very exotic particles. And on the right, what is more familiar to us in the context of this talk would be the kaons. The kaons can have one strange or anti-strange quark. So as you see, K plus, K minus refers to the electric charge of this system. And also you can have, these are called mesons. By the way, the amount of particles that the quarks can meet together is quite impressive. I can list here two tables with all baryon and meson on the left and on the side respectively together. And so the idea which kind of I try to convey with this long introduction is that we can, using kaons, so this system with strangeness inside, with a strong quark inside, can be our kind of charting tool for these new territories in the nuclear frontier. And in order to understand better, so how do we chart? Well, our pulsars in this case are so-called kaonic atoms. So the kaon is a rather heavy particle. It has also a small but appreciable lifetime. So what happens is that if you have one kaon, which is traveling through matter in general, it can be that it forms a metastable state with a nucleus. So you can see here that because of the, you see here there is also an electron. The electron interacts only electromagnetically with the nucleus. The kaon, on the other hand, since it is also a meson, so it interacts via the strong force via quantum electrodynamics, then also is affected by the interaction with the nucleon itself. And this means that since it is so big, so heavy that it gets closer to the nucleus, and also is also affected by the strong force. Something which for normal, so ordinary atoms doesn't happen, because the electron does not have does not interact strongly. And so kaonic atoms are really the ideal tool for this kind of charting job, especially to understand the kaon nuclear interaction regarding the scattering and nuclear interaction. So, but they are also connected with the dark matter studies. So could be that the dark matter is explained by self-gravitating strange dark matter, for example. I'm not going to detail into that. And they are also important for fundamental physics. As we said, in order to understand the equation of state of the neutron stars. And finally, they also have an extremely high impact on how we understand what is called low energy QCD. So low energy, strong interaction in the limit of the chiral symmetry, and on lattice QCD. So they have really huge and vast implications in physics. And so how how do we use them to study this? Well, so on the top sketch, you can see a kaon, which gets around an atom. So first it is initially captured, so it expels a Auger electron, and then it performs a series of transitions, so cascades toward the most fundamental level. And this is also shown on the right of this, on this plot here. So until it's far away from the nucleus, then the transition are not so much affected by the presence of the strong force, the interaction with the nucleus. But as soon as it gets to the fundamental level, then this force cannot be neglected anymore. And indeed, it shows up in this kind of transition with a different level of energy and also a broadening of this transition. So you can imagine each of these transition happens with a photon release. So we are speaking about X-rays emitted with a very peculiar and smoking gun of this exotic system. And in order to study these systems, the Siddharta collaboration was born, and this is a collaboration of several research institutions in Italy, Austria, Romania, Germany, Japan, Canada, Croatia, and Poland. So as you see here, is financed by the European projects and the INFN and all the others. And so I promise this is the most math in this kind of talk. So the scientific goal of the collaboration is to perform the first measurement of the kaonic deuterium. So in the sketch before, I showed you a nucleus with many protons and neutrons, but actually what we are interested in with this experiment is a kaonic deuterium, so only one a proton and neutron. And of course, this way we can determine what I said before, namely the shift and broadening and width of these X-rays to the fundamental level. And this is extremely important because once you have this epsilon and gamma, so the shift and width of this X-ray of the fundamental transition to the fundamental level, you can completely solve the scattering length of the kaon to proton and neutron. And this is because a previous measurement, I also will give a bit of detail, previous measurement of the Siddharta collaboration in 2009 was able to measure the kaonic hydrogen, so a really simple system which then unlocked this kind of observable, which is the interaction of the kaon with the proton. And indeed, this has been a long journey, and I will say maybe another couple of times during this talk that the journey sometimes is also maybe the nicest thing you do when going on a trip somewhere, and this has place both at Dafne, where I'm now working on this Siddharta experiment, which through the year was realized in the DR experiment, the Siddharta, as I mentioned, in 2009, and the very recent, which we are still operating, still in data taking, the Siddharta-2. And also a parallel effort on J-Park, which is another facility in Japan, is very active in this sense in kaonic atoms. And so some brief words about the Dafne collider. This is a truly remarkable machine we have here at Frascati. And by the way, my office is here on the bottom of this picture. And as you see, the first step of this accelerator is called a LINAC, which is a linear accelerator. And the accelerator uses electron and positrons, which are then injected into the Dafne collider. where they are collided at the energy which is the same as the one particle, which is called the phi resonance. The phi resonance is special because it decays half of the time to a pair of kaons, so k plus, k minus, or k neutral. And the properties of this resonance is that the mass is almost the same as the combined mass of the kaons. So the kaons have very low momentum, 127 MeV, and they are very monochromatic. So their dispersion in momentum is less than 0.1%. And this is an image of the inside of the accelerator. And so you see here so you're looking at the center of the accelerator from outside, and these are the injection lines which brings the electron and positrons inside the machine. And so I prepared a little slide to explain the experimental principle. So what you have in this kind of accelerator is electron and positron collide at the center. So the center is called the interaction point. And here is where the phi resonance is produced and decays almost instantaneously. And after it is decayed into kaons, k plus, k minus, some of these kaons could go in one direction, where we have put a cryogenic target. This is showing what we call the target, and inside can have gas, for example, deuterium for our deuterium measurement, but also other gases. And the detection principle is very simple. So since you have two objects coming from one center, then you put above and below two detectors. These detectors are called scintillators. And then if you see two particles traversing the scintillators at the same time, it means that most of the time this will be our kaon, which will be then entering the target, and it will form a bound state with the atom of the gas and perform the transition. So this is again what happens inside of the gas. So you have the kaons, which is capture and then cascades through the fundamental level, which is again, I repeat, has a different energy and broadening of this, which you see this photon, which is then detected. You can see also in this other animation, is detected by other detectors. In our case, they are X-ray detectors called silicon drift detectors. And why we do all this with all these scintillators, etc.? Well, because this is an accelerator, so you have a lot of particles coming from the beam lines. You have activation of various metal parts inside the vacuum chamber and the experiment itself. So in order to be sure that you are really selecting your kaons inside, you want these two detectors which act as a trigger. In fact, we call them kaon trigger. And so this is a kind of another way to summarize the benefits of this approach we have at the Dafne, that we have these low energy kaons, so we can use gases. They are monochromatic, but one drawback is that, of course, the phi doesn't decay with k minus necessarily in the direction of your target, so you are wasting a lot of kaons which go in other direction. This is a problem of acceptance of efficiency. On the other hand, what is done in JPark is that you can produce kaons not from the phi as done in the Dafne, but from a secondary beam of a proton beam. So you smash a proton into a wall, and it will produce a lot of particles. And actually, quite some of them will be kaons, which you can select with magnetic fields and collimator, for example. And then, in both cases, you direct this beam of kaons inside your target, as I showed before. And this is an overview of the very first experiment of the Siddharta collaboration, the Siddharta. And this is an overview of the silicon drift detectors I mentioned before. I will also talk a bit about them. And the schematics here is really the same as showed twice before. So you have this electron positron, they collide at the center of this interaction point, and you basically wait for some of them to make a transition which is detected by the silicon drift detector. And I mentioned that the Siddharta produces the observation, the measurement of the kaonic hydrogen. And this is really the result which is shown here. And you see in this spectrum, so you have the energy of the X-ray, which are detected as an histogram. And you see that from purely electromagnetic force, the electromagnetic value of the K alpha line, so the fundamental line of the hydrogen, would stay a little bit off with respect to what observed. This is, of course, because what I told you before, this influence of the strong force on QCD from the nucleus on the kaon. And in fact, we observed almost 300 electron volts of difference with respect to the electromagnetic value. And also on these plots are visible the other transitions, so not only the fundamental K alpha, but also K beta and the higher part of the transition. And so again, this gives a bit the idea of why it is so important to measure deuterium, because after the kaonic hydrogen measurement was performed, you see on the top of these plots, they are showing as a function of the energy, the agreement of different models. So different models which were built in order to explain the kaon proton in the bottom kaon neutron interaction. As you see, after the Siddharta, they were able all to set to a common point on this line, which is the threshold energy. But actually, so since it is missing still, this missing part of the puzzle, the kaonic neutron, the kaonic deuterium, there is still a big disagreement on all these models. Their models are from Bonn, Murcia, Praga, Kyoto, Munich, for example. They all predict different values. And so how you do this kaonic deuterium measurement? So similarly to the kaonic hydrogen one, you see you have your expected electromagnetic interaction, but what it actually observes is the influence of this strong force from the nucleus. So there is a epsilon and gamma, the shift and the width of this transition is deformed by the interaction. And this really can pinpoint which of these theories is correct. But so far, since we don't know, this is the reason we are investigating this sort of system. And in the same plot as before, this is the shift and width, so how much this transition is deformed in energy and enlarged with respect to the electromagnetic one. All these models, they do not have an agreement. As you see, even recent ones, they predicted very different values and so on. With our experiment, we can achieve a precision which could be able to confirm where this interaction is taking place, in which part of this plot, and finally confirm or not the models which are around. And so this is a image of the Siddharta-2 experiment, Siddharta-2 apparatus. As you see on these blue rectangles, these are the kaon triggers, the one we use to identify really, okay, this is a kaon entering my experiment, and we have the target, as we saw, with the gas inside, where the kaons make their bound state with the atoms, and all around we have 384 silicon drift detectors, which are the optimal tool to use in order to understand the energy of this X-ray. Finally, all around, you have a lot of subsystems, which we call VITO, and the job of the VITO is to basically understand if other particles are coming from outside, from the accelerator line, and to say, okay, this event is likely coming from not from kaon, so you can neglect it. And this way we can perform a very clean measurement, even of precision spectroscopy, even in a very hard environment, radiation environment of an accelerator. And so the silicon drift detector, they are like this here, shown, the one we use in Siddharta. Each array has 8 SDD units of 0.64 centimeter square. So with 48 arrays, we have quite a large active area, and plus they are quite thick, so 550 micron. And this, of course, because you want to be sure that the X-ray is really captured in the region of interest of our experiment by the detector. And on the right, I'm showing some schematics of how these are, how this works. So both top and bottom, you see they have this geometry with anode and cathode. And what happens basically is that you have a X-ray which ionizes some point inside, at which point the charges are divided. One will go to the anode and the other to the cathode. So in this way, you can study the voltage output of these detectors and see the energy of the X-ray. And these silicon drift detectors are extremely stable and good at this job. And as you see here, I'm showing some plots. This is called linearity. So it means that the response of the silicon drift detector is very stable across all the energy range of the of interest for the Siddharta collaboration. And also the resolution, which means how good you can resolve some individual transition, is quite good. It's 160 at the line of the iron. And they are very stable. As I said, here you can see how much it drifts the position of the iron. It's very few, less than 1 electron volt. And the timing is very important, as you could have imagine from this, from also the other slides, because you can really pinpoint the exact moment of the kaon forming the bound state, and this is also quite good, 450 nanoseconds. And so the kaon trigger I showed before in the animation really can select the kaons not only by coincidence but also by time of flight, because these are, as I said, the kaons are quite massive, 500 MeV, so which means that lighter particles will be faster than them. So you can separate, as you see in this plot. I'm not going too much into detail, but you can really separate the kaons from other particles really by only timing. And this is a typical spectrum, which is collected by all the SDD before the application of the trigger. You can see basically what are spectroscopic lines of elements close by to the detectors, this bismuth, copper, and so on, titanium, and so on. And also you can notice that the events in this plot are really a lot, so billions of them. So from this, it's not really much visible. So what you can do is then you apply one by one all these cuts from the trigger, which is the most stringent cuts, but also time of flight, drift time, which is basically this timing of the STD, and all the veto. In the end, from this whole billions of events, you are left with not so many anymore, but you can see the emergence of some additional lines. So this is a kaonic carbon. So when the kaon forms a kaonic atom with the carbon which is present in the entrance window of the target, we are able to see that. And you see and distinguish the different transition of kaonic carbon, 5 to 4, 6 to 5, and so on. And just to also add something that last year, so 2 years ago, 2021, we had in place a smaller version of Siddharta-2 just to check that everything works, and indeed everything works. And so we were able to measure a kaonic atom, which is the kaonic helium-4, which is extremely visible here on this peak, and this was actually is actually one of the most precise measurement of kaonic helium in gas. And you can see also all the other transition, kaonic oxygen, carbon, and so on again. And we also did the characterization of the intensity of this kaonic helium-4 as a function of the gas. Of course, you expect some change as a function of that, and we published also that. And finally, with the Siddharta-2 last year, also this is another plot showing which was published this year, showing all the spectroscopic line we can resolve with this approach of the kaonic atoms. And these are even the M lines, which go all the way at low energies, of course. And this was the very nice analysis which a PhD student did on the kaonic M lines. And these are a few pictures of the experiment on bottom left from above the beam pipe. So you see the positron and electron line. This is part of the collaboration on the top right. On bottom right, you see kind of this beautiful picture of all the silicon drift detectors, which are then installed inside here on the top left. These are again some scintillators, some read by silicon photomultiplier, and which are placed all around the silicon drift detector, so you can find. And this is the open vacuum chamber of the Siddharta experiment. And actually, a few weeks ago, 3 weeks ago, we did the first kaonic neon measurement, and this is quite interesting because it can be used to check that everything is in place for the kaonic deuterium measurement, but also has a very important implication, because from that you can, from higher transition, you can measure the mass of the kaon. The mass of the kaon has an artificially large uncertainty. This is because the two most precise, this plot is from the PDG, the two most precise measurements actually do not agree with each other. So if we can manage to measure from kaonic atoms with sufficient precision the kaonic mass, the kaon mass, then of course this picture would change and the uncertainty could decrease drastically. And this is again another view of the Siddharta-2 experiment as ready for the kaonic deuterium, taken from inside the Dafne collider. And we expect something like that. We need quite a nice amount of luminosity, so 800 inverse picobar. And this is kind of the expected spectroscopic spectrum which you would have, of course, in simulation. And what we will extract from there is, as I said again, the shift and width, so with connection with the scattering amplitude and implication to all this physics which we discussed before. And so also important to see what we will be doing after Siddharta-2. Well, more conic atoms, of course. This is motivated by the fact that many, if not most, of the measurements of conic atoms are back the 80s or even the 70s, as you can see in these plots. From of the width and shifts or different as a function of z. And this data is actually used by all the theoretical models to, for example, predict the nuclear interaction or three-body interaction at threshold, nuclear density distribution, and so on. We've seen. So this is critically to make sure that these measurements are the most precise possible and the most up to date. And in addition to that, these old measurements, they have very large uncertainties, and many of them coming from very different and hard to compare experiments are hard to put together. And also the yields, which means how many of these transition you expect, are basically unknown for except few transition. And oftentimes when collaboration measured it again, the results were also quite different. And we also want to, we will also plan to perform this measurement, and this is within the Excalibur project. And this we propose to continue after we are done with the deuterium with all other Z materials, so intermediate and heavy, conic atom, and so on. And this is what it will be looking like. So of course we are already planning to use much more detectors for example the high purity germaniums, which you see for here on this sketch, where inside the target you won't have the gas anymore, but for example solid targets. And in order to be sure we can measure this transition, we are developing again in collaboration with the Politecnico Milano and FPK and NFN a SDD which is more than twice the thickness of the one we currently use. Of course, this means we can go higher and higher in energy of the X-ray. And there are also several other projects where, for example, cadmium zinc telluride detector can be used. Actually, one of them was installed last week in Dafne already as a preparatory study. And also we already have one KPG high purity germanium inside. And so this brings me to the conclusions. So as I try to convince you that conic atoms are really our lighthouses for charting new territories in strangeness. And Siddharta-2 is playing a major role in shaping how we understand and study these exotic objects. We are in data taking, and we are performing the conic deuterium. So this will allow us to theoretician to completely solve the kaon nuclear interaction. And this is of course important because has many implications, as we saw, from neutron stars to dark matter and fundamental physics. And so that's it from my side. Thank you a lot for the attention. I leave you the word, Catalina.
Thank you very much, Fabrizio. That was a fascinating presentation of the activities which are undergoing in one of the labs and facilities which are receiving transnational access from the Strong 2020 project. And while we are awaiting for questions, those who are having some questions or curiosities, just write them down in the chat and we will try to answer those. I want to ask you, Fabrizio, what would be your biggest hope, let's say, related with measurements which can be done in the future at such a strong and beautiful facility as Dafne is?
Thank you, Catalina. This is a very important question, I would say. So, as I briefly mentioned, all sort of conic atoms are very, very important to assess the properties of physics objects which are not so well understood. One experimental effort which I particularly like, for example, is determination of the mass of the kaon, and I think this will could also and indeed has a big support because it will propagate with the reduction of uncertainty to many analyses in other fields, for example, in high energy physics and many more. So what I also want to underline is that we know what are the advantages of this effort, and it brings to the strangeness. But also the journey is important in the sense that we continuously find new ideas and approaches which can be really game changer for not only for us but for many. So this is I think continuing this effort for a long time at Dafne would be beneficial for many aspects of physics, of modern physics, astrophysics, you name it. It's really impressive what can be done with the conic atoms.
Absolutely. And since you're mentioning the Dafne accelerator, which never an accelerator works alone, so we also have to say that at Frascati there is a very strong group of accelerator people who work to keep the accelerator alive and improve it steadily, to which we are really very in depth, because if a facility is supported from an European project, of course, you need to have something very strongly to support. Would you like to say something more related with an accelerator like Dafne?
Yeah, I also want to second that. It's an incredible work they've been doing in this year with the commissioning of the Siddharta. So really, a lot of thanks, and whatever can we say to thank you is not enough. So if someone from Daphne is connected, that is really impressive. It was managed to be done to reach such a level of precision, of high luminosity and background conditions of a machine is really not trivial, and it's really an effort which propagated from the years, really. So it's a major effort from many years, and I really want to acknowledge that and to thank everyone involved really a lot.
Absolutely. So this evening we presented to you one of the projects which are supported within the European project Strong 2020, in particular one of the facilities out of the 6 facilities plus the ACT STAR at Trento, which are supported for transnational access within the Strong 2020 European project. And I don't see questions in the chat. However, if any one of you would have some curiosities which might also be appearing after we are now in direct, so we are connected with you directly, please send a mail. You can find the email in the chat. But before concluding, let me also thank to the Frascati National Laboratory team who is allowing us to do these public lectures. And I want to ask Deborah. Deborah, are you there as a representative of the Dissemination and Education Office in Frascati? So maybe, Deborah, you can take away the slide of Fabrizio. So perfect. Now we see you very well. So Deborah, thank you very much for allowing to do these public lectures. You are always there for us, and yeah, what we can only thank you.
Thank you.
Good. So we will continue with our public lectures. Just stay tuned. And since I don't see additional questions in the chat, those who are curious, send us emails. And of course, we also invite you to come and to see our laboratory and our facility in the various occasions like the Open Lab or European Researchers Night, where you can meet also Fabrizio, myself, among the others. And thank you once again, Fabrizio, for bringing us in these new uncharted yet territories, which we hope to be able to chart and to expand the knowledge we have in the field of nuclear interactions, of the strong interaction with strangeness. And let us all together to wish to those who are watching us a very nice afternoon, and stay tuned. Thank
Bye.
you.
Thank you. Bye.
Bye.
Bye-bye.